Hello? Can you hear me?
Hello? Can you hear me?
All right, I can hear myself.
All right.
So we'll
I can
probably
hear
get
myself.
started in a few minutes here. Just let more people trickle in. Oh, hey, Carter. Okay, a message just went out in the Discord, so we'll wait a few more minutes. All right, so I'm looking at just the results of the poll that I put in the chat. I don't know how YouTube Live works. Can you like see the chat before that was there before you joined, or do I need to repost that for people just coming? Um, I guess I'll just post them again, but those are just sort of to help me know what to talk about, because this is a pretty general talk. So looking at this so far, most people are interested in design. Graphics is pretty high up there too. That's good. Following kinds of games, people don't really care. That's perfect for this talk. We're not talking about any specific kind. And 1 hour, 1.5 hours is fine. So the goal is I'm going to try and get through this in about an hour. And feel free to ask questions, um, as you have them. There are a few people from ACM in the chat who should be able to answer some basic questions, and if they see any questions that are more advanced, they can give them to me, and I will either answer them right then if they're relevant to what we're doing, or I might wait until the end if it's sort of a tangent that I can go on. But we will have sort of a Q&A session after the presentation, um, just for everyone to ask questions and talk about more specific things. So with that, let's get started. My name is Hayden Allen. This is my first semester at UTD, and I like to consider myself a self-taught programmer. So just some background about myself. I started learning to program near the end of 8th grade, and I pretty much haven't stopped since. All throughout high school, I was writing games and tools to make games, stuff like that. So most of my experience is not actually game design, but rather, I guess it's more game programming, specifically game engines, I guess. And in terms of teaching, this is not really the first thing like this that I've done before. I led my school's UIL Computer Science Club in high school, and I taught a fair amount of the senior level class. So before I forget, actually, I'm not sure if this link was posted anywhere, but the idea for this workshop is I have this sort of presentation. I just put the link in the chat, and I'll be reading along with it just to sort of explain stuff to you. But it also contains these snippets of code, and it should have all of the code that you guys need to reach the end goal of this presentation. And that's how I'm going to be doing it too. So I'll be reading from this and just explaining a little bit about the code. And then in the interest of time, I'll just copy and paste that into my own document. This just makes it faster and it makes it easier so that people don't get stuck on some random thing and we have to take 5 minutes to figure out what's going wrong. But I definitely recommend following along and actually writing this with me, just because I think that doing is the best way to learn. And near the end of the presentation, I'll show you there's a link where you can download this actual, like a zip file containing all the code that we're going to write, and it's all commented. So you can sort of go back there afterwards, and it has a line-by-line rundown of everything that's happening. All right, so let's go ahead and get started. Sort of like I said, this is not really about game design particularly. It's more about game programming. So I'm going to give you a high-level overview of basically the biggest parts of literally every game. So graphics, getting input from the player, and we're not going to do audio, actually, just because we're doing this in JavaScript. I'll talk a little bit about that later. So graphics, player input, and then we're going to do some collision prevention, because that is important for basically any game. I don't think I've ever seen a game where you can just walk through everything or something like that. So like I said, this is all in JavaScript. So all you need to do with these code snippets is bring up an editor. I'm using Atom. You could also use like Visual Studio Code or Notepad++. You could do Notepad if you want, but that's pretty prone to mistakes. But yeah, so all you need to do is paste the code in here, and then it's going to be an HTML file, so we can just run it in the browser. Super simple. And the reason we're doing this is just because JavaScript is, I think, the easiest language to write in, and it has a lot of sort of low-level stuff built in, so we don't need to worry about setting up a window and boring stuff like that. But obviously, if you were making, an actual game engine, you wouldn't want to write it in JavaScript because it's slow. All right. So let's start by considering some of the features we'll need for any game. This is sort of what I was saying, is every game needs graphics, input, audio, which we're not going to talk about, and collision prevention. Because I'm not going to talk about audio at all, I will give a little note about it up front, is that the reason I'm not talking about it is all you have to do is play a sound through the browser. It's like one line of code. It's super easy to do, and there's just nothing to say about it. But if you were writing a real game engine, in quotes, you'd probably want an audio library. I've used OpenAL in the past, and you might have to set up some sort of system that like streams audio from a file if it's a really long file. You don't want to just cache all that into RAM and have it sit there, basically. But once again, none of this interesting stuff is actually possible with JavaScript, so we're just not going to talk about it. We will start with graphics, and then we're going to work our way down the list. So before we even get into graphics, we need to just like set up the actual page. So we'll just copy this bit of HTML. All this does, this is like the bare bones thing you need, and it just sets up a canvas, which is a neat little HTML element that will let us draw to the screen. So I've made a project folder here. I'm going to make a new file. I like to call it index.html. I'll just go ahead and paste that. And then if you go into your file system, we can, here, I'll just show you. So this is the folder where I have it. You can just double click on that file, and it should give you a blank screen. The first thing I recommend doing is pressing, if you're on Windows, Control-Shift-J. If you're on Mac, I think it's Option-Command-J, or maybe Option-Control-J. I don't exactly remember, something like that. And that'll bring up this little console. And we can print some debugging output here if we want, but most importantly, it'll show you errors, and it'll give you a description of where you've written stuff that has messed up. But for now, it should just be blank, and we should have a blank screen. Okay, so that's just the HTML file, and this is pretty much all we're going to do with it. We're going to write all of our JavaScript code in separate files, and then we can include those files in this index.html. So the first file we're going to make is called global.js. It is just pretty much a container. It has a single object called global, and that's just going to store global variables and global functions, so things that we want to use in various places throughout our program. This object just helps keep them organized and in one place so they're easy to find. So for this one, I'm actually going to make a folder called scripts. I like to put all of my JavaScript code in a separate folder. I think it just helps me organize it, but this isn't a massive project or anything, so if you want to leave it in the same folder as the index, it'll be fine. So I'll give you a little overview of what each of these does. So if you noticed in the index file, we have this canvas tag, and we gave it an ID of C. And all this does, pretty much, is let us get this element, get a reference to this element in JavaScript. So that's what this document.getElementById does. It just gets the actual canvas. And then the canvas itself stores a bunch of information that is not necessarily relevant to drawing on the canvas. For example, you can see down here we manipulate like the width and height of the canvas and the CSS style of the canvas. But to actually draw, you need to get a drawing context. And all of the stuff we're going to do is 2D, just because 3D would take way too long to explain, and I really don't have that much experience with it. If you are writing this by yourself and not just copy pasting from the web page, that's fine, but make sure that this D is lowercase, because for some reason, if it's capital T, it won't work, and that can be frustrating to debug. Then we just have an FPS thing here. I've set mine at 144. We'll use this in just a minute. This is sort of the target refresh rate of our program. And then we have this init function here, which, like I said, it just resizes the canvas to a nice size. It's just a square 800 by 800, and it puts a black border around it just so that we can see it instead of this white page. All right, so that's all we have there for now. We're going to come back to this quite frequently and add stuff to it. So the first thing to do every time you make a new script is go ahead and include it in the actual index file. So you can do this with the script tag, and you set the source property, src, to the relative file path of the script you want to include. Oh yeah, and for some reason that breaks the syntax highlighting. But there we go. So now I've included this. And we can refresh the page here. Nothing's actually going to change yet because we haven't called the init function. We'll do that in just a minute. So let's make our driver code. So this is sort of, in a way, it's kind of the opposite of our global thing. So the global one we want to include before every other file, right? Because we want to make sure that this stuff is available to all the other files in our program. The main file, which I'll create right now, we want to make sure we include that last because that needs to use everything else in our program. So I'll include that afterwards, and then the very first line I'm going to write, I'll just go ahead and copy it from here, is global.init. So that'll resize our canvas, give it that black outline, and then I set up the game loop here, which I'll talk about in just a second. But let's go ahead and copy paste this, save it, and make sure that you include it in the index file after global.js. And once you've done that, if you refresh the page, you should now see a mostly white screen with a black box. So that black box is just the outline of our canvas. So yeah, that's pretty perfect. So now let's talk about the game loop. So this is pretty simple. We are going to be editing this quite a bit. This is just where like the actual game runs. So most of the code we write isn't going to be in here. It's going to be in other files. But we are going to use the code that we write in other files here. This is what runs it. And you can see I've given these sort of comments here that just gives you sort of a layout or a play-by-play of what happens each frame. So first we need to clear the screen, so get rid of everything that was drawn last frame. Then we need to get input and probably do something with that input. Then we need to draw stuff, draw the entire world and the player and everything in its current state. And then once we've drawn everything, this set timeout call right here will make sure that this doesn't just call itself like immediately. Basically, it'll wait for the time that we've specified so that it runs, or it tries to run at least, at the target FPS. So we're not going to be messing with this. And then there is one initial call down here. Make sure you don't delete this. You do need to call this function once, but then after you call it once, it will call itself over and over again with the set timeout function. Okay, so let's actually start drawing something. So we're sort of just going to run through this in the order that I have the comments listed here. So the first thing we're going to do is clear the screen. That happens every frame. So I'm just going to go ahead and copy this and throw that in, throw that in the global file. So I have this color here, clear color. It's just a hex code for pure blue. And then I have this function clear, and this calls global.ctx.clearRect, which actually clears the screen. And then we set the current color to draw with, and then we draw our blue rectangle over it. So these two lines down here are totally optional, because once you clear the screen, that's like the main thing this function does, is it actually clears it. But this just helps you sort of visualize where stuff is being drawn, because if you don't do something like this, then you're going to get a white canvas and a white page, and it can sort of be difficult to see what's actually being drawn. But if you have sort of a color that's a background that's a really garish color, then it's really easy to see where stuff isn't being drawn properly. So I'll give you a little bit of an overview about these functions really quick, because it applies to more than just these two functions. So the arguments they take are x, y, width, and height, in that order. So you can see here I've specified the x and y as 0, 0, and then the width and height as the width and height of the canvas. So that means that every frame I want to clear a rectangle the size of the entire canvas. And then I use the same coordinates down here to draw a rectangle the size of the entire canvas. Now these units are in pixels, but they can be, they are, it's JavaScript, so there are no integers. It's all floating points. And that's not really something we're going to talk about here. There is a bit of weirdness with how that works, but basically just know that the unit is pixels and it's x, y, width, height. Another quick thing to note about the coordinate system is that the positive x direction is to the right, which is what you'd expect, but the positive y direction is down. And that's important because of what this actually does. So this says we want the top left corner of this rectangle to be at these coordinates, 0, 0. And then we want the width, or the number of pixels to the right of this x coordinate, to be this, and the height, or the number of pixels drawn down from the y coordinate, to be this. So every rectangle starts in the top left corner, and it draws to the bottom right corner of the rectangle. Once you get the hang of that, it's pretty intuitive. It's just something I thought was important to note because, like in math, when you're actually graphing functions and stuff, usually positive y is up the page, but in this case, it's down. Okay, so now that we have that function written, we can go ahead back into our update function in main and just call global.clear. Very simple. And now we should get a solid blue screen, which is not very interesting, but at the very least, it's proof that what we've done so far works. Okay, so now let's start drawing some stuff. We are only going to draw and really only going to talk about rectangles at all. I'm not going to talk about any other types of polygons, especially once we get to collision prevention stuff. The math for that gets really hard, for lack of a better word. It's just a lot more involved than what we have time for. And so we're only going to talk about rectangles, but that's fine. You can make a really fun game with just rectangular based stuff. So we're going to start by just drawing single color, solidly filled rectangles, just like our blue background is. We're basically going to copy and paste that code and make it a function. So the function is called rect, and it takes the x, y, width, height arguments in the same order, and then c, which is a color. So it sets the fill style and then draws a rectangle at the specified coordinates. So we can use this now. I'll just put it under the draw stuff comment for now. Global.rect. I'll put it at 0, 0. I'll make it 50 wide and 50 high. And I'll make it red. And I think, yeah, all of this code I'm using should be here. I guess I'll go ahead and do this. So we can also move its position with a variable. So I'll say x starts at 0, and then every frame will increase x by 5 pixels and draw it at that position. So now it should be moving diagonally down the screen. And boy, it's like really fast. You might have to refresh it a few times to actually like take note of what's happening. So this part is pretty important. So make sure that you're sort of following along with me here and try to track the red rectangle with your eyes. Because when you're just looking at the blue background, it looks pretty fine, like the movement looks smooth. But if you actually track the red rectangle, the movement is really jittery. And the reason for that is that some frames just take longer due to, you know, various system operations or whatever else Chrome is doing at that exact moment. And so some frames take longer than others. And the problem is we're adding exactly 5 pixels to our coordinates every frame. But if some frames take longer than others, then you get jittery. And we need to avoid that. That's like really important. That's pretty much essential to any game, is you need smooth movement. And the best way to do this is to keep track of the difference in time between the last frame and the current frame, and then scale the amount you're moving it relative to that time delta. So I'm just going to go ahead and take this code here, which creates an object in global called time. And that has 3 parameters, now, or 3 fields, sorry, now, last, and delta, which we'll talk about in a minute. And then I'm going to add these 3 lines of code to my clear function, because we want to update the time of every frame. And we're calling the clear function at the start of every frame, so this will run every frame. So what this does is it gets the current time, which is in milliseconds, important to note, and then it calculates the difference in milliseconds between the current time, time.now, and the time at the start of the last frame, global.time.last. And then, of course, we set last equal to now, so that next frame when this runs, now minus last, will give, you know, a real value. So now that we have this, we can go ahead and scale our movement by the frame delta. So instead of just plus equal 5, we're going to have plus equal something times global.time.delta over 1,000. This might be kind of confusing. I'm sort of just going to breeze through it though. The over 1,000, I use that for convenience because all of the measurements of time are in milliseconds, and it's easier for me to think in terms of seconds. And so this just says 100 pixels per second, basically. That's what this says. And yeah, I mean, you could just multiply by time.delta, and then this would go like way too fast for you to even see. But it's easier for me to think in terms of seconds. So now if we run this, it should be slower, but it should also be smooth. So that's good. That's a start for sure. But the issue really is when it's fast. So let's check. I'm going to turn this up to 500 instead of 100. And it should be really fast now. And if you track it, it's not totally smooth, but it's much, much better than it was. And really the only part about it that's not smooth right now is the fact that at a certain point, you're just moving multiple pixels per frame, right? So it's going to jump around. But at least it looks like, to the human eye, that it's moving about the same amount of multiple pixels in real-world units, right? In meters per second. It's not in frames anymore, which is what it was before, and that's what was causing the jitter. So all the movement we're going to do, we're just going to scale by this. It's pretty simple, but it's very important. Okay, so now we've got a red rectangle. It's pretty boring, though. It's just like a solid color. And really, in any game that I think I've ever seen, unless it's like a super simple Flash game or something, you're going to want textures. So we will add this function to our global, which is very similar to the rect function. You can see it takes the arguments in the same order, x, y, width, and height. The only difference is it takes an image. And this parameter must be an HTML image. So I'll show you how to create one of those. If we do, I'll just call it image for now. So we could do let image equals new image. So this creates an empty image element, and it doesn't currently contain any data. In order to assign it to an image file, like from our file system, we do image.src and then the relative file path. So I will create a new folder called res for resources, and then very quickly I'm going to make just a terrible little pixel art character guy that we can see moving around on the screen. So I've included a link, a shameless plug, to my own very simple sprite editor on my website. There are 9999999 billion different better ones out there if you want to use those. So please do. But the main thing here is that we make sure that it's something that is not just a solid color rectangle, right? Because that's what we're changing. We want to actually draw something kind of interesting. So I'll just have my little guy here. I'll give him that's a really fat face, but whatever. So I'll just call him player. And then I will save the file. And if you'd prefer, you can just download some image from Google Image Search or whatever. It really doesn't matter at all. So once we've downloaded that, I will take the download file and move it into my res folder. And now in Atom, I should see it appear over here on the side. And you'll see the same thing in Visual Studio, or VS Code if you're using that too. So basically what this did now is I have an image and I assign its source to this file path. And now that I have an actual file at that file path, that's valid. So we'll check this by commenting out the global.rect call and replacing it with a global.texture. And we'll use the same coordinates, but instead of this color here we were doing before, it was red, we'll send it the image. And all of this code is on the presentation if I'm going really fast. But now if we reload here, we see we have a little guy moving across, doing a T-pose. There we go. And pretty much that's all we have to talk about with like the actual graphics side of things. So this, I mean, you could make it more efficient. You could set up a system like if you had a really large game, for example, where if you had a bunch of things using the same image, you wouldn't want to create a bunch of copies of that image. So you could have a pretty simple caching system. And yeah, but again, this is sort of a general talk. So I'm gonna try my best to avoid going on tangents like that. So I see a question here. Which file did you put that code in? The code to draw the image. Is that what you're talking about? Yeah, so that's in main. I just replaced the global.rect call that we were doing with a global.texture call. And it should tell you... it doesn't actually. That's a good point. It's the idea is that there's the file name of the file of all the following code above it, but clearly that is not the case. Let me edit that real quick. That's annoying me. All right. There you go. Okay, so now that we have our graphics working, we need to sort of take a step back and figure out how we can scale this up to the size of any arbitrary game. Because drawing one texture is great, but you're going to need to draw a whole lot of textures, and you're going to have to draw them all every frame if you want to have an actual game. So right now, let's do some simple counting here. We have 1, 2, 3, 4, 5 different lines of code to draw a single texture. Now, if we want to draw even just 50, which is like, I don't even think you could fill this tiny 800 by 800 window with 50 textures. That would be insane. 50 times 5, that's like 250 lines of code. So basically our problem is we know how to draw stuff, and we can do that. It's really simple, but we need a system that can contain a bunch of stuff and then draw it all at once. Just organize it so that we don't have to write every single line of code to draw every single thing. And this is the basic principle behind a rendering pipeline, which is a pretty general term. So if you attended George's talk last weekend, I think, on computer graphics, he talked about OpenGL. And OpenGL's rendering pipeline is very different from the one we're talking about, where you have vertices on the CPU, you send it to the GPU, and then every frame those vertices are passed into a vertex shader and then a fragment shader, and then finally you actually get pixels on the screen. So while this rendering pipeline, or at least one very similar to this, is definitely happening sort of behind the scenes on our canvas here, we don't have to worry about it, which is great because we're just trying to write code really fast. So this rendering pipeline definitely exists somewhere in here, we just don't have to write it. So I'm going to be talking about a higher level kind of rendering pipeline, one where we store map data or world data, texture data, whatever you want to call it, and then can easily draw it to the screen all at once. So the goal here, we have the code to draw one thing, but we're going to abstract it to the point where it's easy to draw many things. So we're going to create a few classes to help us out with this. The main one is going to be scene. And this is the one that is actually going to store all of the world data. In this case, unfortunately, because this is such a general talk, I can't really, there's not a best way to store world data for some arbitrary game. Depending on the kind of game you're making, you'll definitely want to optimize how it's stored so that when you're actually drawing it, it's much easier and much faster. But for now, unfortunately, we're basically just going to put all of it into a list. But we'll get to that in a minute. The first step before we actually start making this world data is to define the unit for that world data. So right now, what we need to draw is we need an image, we need some coordinates, and some dimensions, and that's it. So we're going to take these, I think 5 or 6 lines of code here, and basically move it into one new file called tile.js. And the entire file is shown here. We are not going to change this throughout. This is all we need for now. So I'll just paste that in directly. So let me run through this real quick. Right here in our global.texture call in the game loop, we actually pass an image. But this is kind of annoying to write, for lack of a better word, because we actually have to create an image and then set the source of the image and then pass it. So when we create a tile, it would be best if we just pass the file path to the image and then let the constructor handle these 2 lines on its own. So that's exactly what we do. We just pass the string and then let it create the image for us. And then there it is again, x, y, width, height in that order. We just slap those in there and store them. I'll talk about this line in a little bit, don't worry about it for now. And then we just have a super simple function to draw, which is almost exactly equivalent to this draw, or the global.texture in the game loop, with one notable difference. It takes 2 parameters, an offset y and an offset x coordinate. And these are just added to the actual stored coordinates of this tile. And for now, I'm just going to leave it at that. We'll talk about it pretty soon when we look at a camera. So that's that. Now that we have the unit for our world, we can actually worry about storing these units. So that's what the scene class is for. And this is it in all its glory. It's like 11 lines or something. Go ahead and make that scene.js. Paste it all in there. And like I said for this, unfortunately, I'm just going to make it as general as possible. It's literally just an array of tiles, and we're going to draw all of them every frame. But if you have a question about the best way to store world data for a particular type of game or something, feel free to ask. That's definitely one I'll save till the end of the Q&A session. But I'd be more than happy to try and help you figure it out. Okay. So now that we have the scene class, we're going to just make sort of a quality of life change here. and we are going to add a global variable called current scene. Now this will start its value as undefined, because remember, we're including the global file before all of our other files, which means that if we tried to do current scene equals new scene, that will crash because scene doesn't exist when this runs. So instead what we have to do is just set it to undefined, or really any value. And then in the init function, that's where we'll actually create it. New scene. And all this is going to do is make it easy to sort of hard code world data, because if you're making an actual game, you don't want to hard code all your levels, because that means every time you make a change to anything in the world, you have to recompile the entire code. But for JavaScript, it's super fine. Like we'll just run with it. And that's what this line does in the tile constructor that I said I was going to come back to. It just automatically adds a tile to the global current scene when you instantiate that tile, just so that to minimize the amount of code that we have to write right now. Okay, so we have all of that. Now we just need to include these 3 new files. So we have tile. Oh, it's just 2 new files. Tile and scene. Just like that. And now we can test it out. I'll go ahead and in main, I'll just replace all of this stuff with, I'll call it player. Player equals new tile. I'll send it that same file path. I'll start it in the top left, and I'll make it 50 by 50. And then we will replace this update to the x variable, because that doesn't exist anymore. We'll say player.x, just to check that movement still works. And then instead of drawing an image, we will just call player.draw with 0, 0 offset coordinates. So when you get this now, you should just have a little guy running from left to right. This is not Hello? Sorry, my headset died. I don't know what that was. I think because there's no audio playing on my desktop, it like automatically shut off. That's kind of annoying. Anyways, so you should just have a guy running from left to right. There's not much to see here. Just make sure that this does work, because if you get broken at this stage, like we're about to add a bunch of code, and that'll just make it even more confusing. So if you're stuck on something, please let me know now, because it'll be even harder to debug as we go along. Yeah, so we just have a little guy moving. But we have a pretty big problem, which is that if you notice, this guy isn't even moving like that fast. Like he's going pretty slow. If I had to play a game where my character moved this slow, I probably wouldn't be playing it for very long, because it would just be such a pain to actually get anywhere. And this is a problem with the size of our screen, because it's only 800 pixels by 800 pixels, which, as you can tell, is not very big. And so we need some way to essentially artificially inflate the size of our world, because obviously our screen can't, expand without bounds. We could make it cover the whole screen, but then at a certain point you just run into the same problem of, well, there's not enough space to put everything. So the solution is a camera. All we have to do here is set up a virtual camera, which will basically follow the player around, and that will make our world effectively infinite, because it means that as the player moves from left to right across the screen, everything around the world, or everything else in the world, sorry, will translate around him, so you can see more or less from his perspective. So let's go ahead and set this up. I will just copy this code, and then I will explain it. A new file, camera.js, paste. There we go. All right, So all this does is it takes a target, and target is an instance of a tile, and it follows this target around. So every frame before we draw the scene, we will call this update function, which returns the x and y off coordinates. And this is very important. The goal of this function, the update function, it returns the x and y offset coordinates, where if you add these to the player's current position, the player will appear directly in the middle of the screen on the x and y axes. And so I'm going to walk through this a little bit with some algebra. I think I'll open up Paint here for a second. So I have this function, and it looks kind of complicated, but it's not that bad. So let me just draw for a minute a fake screen here. Not great, but that's okay. And then I will draw lines denoting the center along both axes. So our goal is basically to draw the player, which remember is a rectangle, right here, right in the middle of the screen, no matter what. So we can notice some things about this simple diagram. One is that this length here is the width of the canvas over 2, right? Because this whole thing is the width of the canvas. Similarly, this is the height of the canvas over 2. Now, this little bit here, from the y-axis center line to the top left corner of the player, is the player's width over 2, and this bit here is the player's height over 2. Remember, when we say draw the player in the middle of the screen, what we're really concerned about is the top left corner, because we start drawing rectangles from the top left. So the simple math we have here is we need to find some value such that when we add to player.x this offset x value, the value we get is the coordinate of the top left corner on the center of the screen, which is going to be c.width, the canvas, over 2 minus p.width over 2. So we have c.width over 2, which is the length from this left side black line to the red line here. And then to get to this orange coordinate, or sorry, the x coordinate of this orange point, we need to subtract half the width of the player. And using this, we can do some very simple algebra to actually find the offset x value. We now have offset x equals half the width of the canvas minus half the width of the player minus the player's x coordinate, which more cleanly written is half the width of the canvas minus the player's x coordinate plus half the player's width. And we do the exact same thing for the y coordinate that we want, except we replace all of the x's with y's and all of the widths with heights. And you can see that's exactly what we have here. We have half the width of the canvas minus the player's x plus half the player's width. And same for y. And then we just return the x and y coordinate as an object. Okay, so that's the basics of the camera. We're not going to touch this. There's a lot more you could do with it for sort of polishing your game, but for now we'll just have it stick the player right in the middle of the screen every frame no matter what, which is perfect. I see a thing here. Instead of my character going in a straight line, I have a plain white rectangle with a black border. Do you have any errors in your console? You should have something on the right side over here. Ignore the first one. So you fixed it? Your character is not going in a straight line. Is it moving at all? It's moving diagonally. The best I can tell you is copy and paste the code I have in the presentation here. Yeah, so we'll get to that in a second. I sort of jumped the gun on this one. I maybe shouldn't have. I have this actually prepared and written out for you, so we'll get to that in a minute. Don't worry. Okay, so we have the camera class here. That's all finished. And now we have sort of two of the three components of a very simple rendering pipeline. We have the scene, which stores stuff. We have the camera, which will be used to draw the scene relative to the player. And the last thing we need is a renderer, which takes a camera and a scene and actually draws all of it. So I will create a new file, renderer.js, and I'll just copy all of this code here. So this one is probably the most trivial of our classes for this workshop. It's just a single function. So you could just as easily stick this render function in like the global object and it would be just fine. Normally, if I was designing a game with a little more depth, you'd probably want things like UI elements, which are drawn on top of everything else. And I would go ahead and stick those in a list in the renderer, just because they do need to be drawn every frame with the render function, but they're not really part of the world, so they don't quite belong in the scene. And if you were drawing, if you were making a game of some specific type, there would undoubtedly be stuff that you want to do every frame in the render thing. But for this example, which is as general as possible, all we're going to do is update the camera, which remember stores a reference to the player, so we don't have to pass it anything through its target variable. So we're going to update the player, and then we're just going to loop through every single tile in the scene and draw it with the offset coordinates returned from the camera. So we call camera.update, which returns these x and y coordinates. We then store those in a variable here, and we pass o.x and o.y to the draw function here of every tile in tiles in our scene. Okay, so I will go ahead and include these two scripts, camera and render, and then we can test it in our main.js. So I would recommend at this point, because things could have gotten messy, I would just copy all of this code here and just replace everything in your main.js with that. One thing you will have to do though is change the global.time. For some reason, time is capitalized in this example, which is not perfect. There we go. That's easy though. Okay, so let's refresh. Of course, I get some errors. Oh, change the file names too. So I'll change res/new sprite to player.png. And then I'll just comment out this second tile line. We'll get to that in a minute. But first, let's just make sure something's actually running. All right, there we go. So now what you should have is a blue screen with your little player hanging out in the middle. And that's exactly what we want. You'll notice here that in the render loop, we have an update to the position. We are incrementing its x coordinate, but it's always being drawn in the middle of the screen, which is perfect. Now we can test that this actually works by adding another tile that remains stationary. So I'll just use the same sprite for this one for right now. And then if I refresh, we can see that that other tile moves to the left. It'll probably be best if I actually make it a different texture. So let me go ahead and do that for now. I'll just make it solid red and I'll call it box. So I'll save that, move that over to my resource folder. And then instead of the second tile being player.png, it will be box.png. Perfect. So you can see now that the red box is moving to the left and the player is staying in the middle of the screen. At first, this might seem a little bit weird because we're saying that the player's x increases. And if you remember from my little explanation of the coordinate system here, positive x, or adding to x, means it moves to the right. But the only thing moving on the screen is moving to the left. The reason for that is that the player is actually moving to the right. It's just being drawn in the middle of the screen. And so the box, relative to the player, is moving to the left. Very simple. Okay, so that's pretty good. Like, now we have a rendering pipeline. It's very easy to add new tiles. You could see I could copy this line here, say I want another box. I'll put it in a bit of a different position. I can change its dimensions, and it'll draw it and everything, and that moves same as the other one. Yeah. Okay. So the problem with this is that even though we have a rendering pipeline that draws everything for us, and it's pretty good. It's not perfect, but it's pretty good. We can't actually control anything. And I've never played a game where you can't move the player around. That would kind of suck. So the next thing we're going to talk about is input. Now, this input section is a bit more JavaScript specific than the previous ones, unfortunately, just because how we get the input has to be a very specific way. But I will introduce a concept that you can use, and that I have used in every input system I've ever done. But just know that this sort of window.onKeyDown thing here, obviously that's only going to work in JavaScript in the browser. So I'm just going to go ahead and take this and paste it at the very bottom of my main file. So what this does, what we do here, is we just have a variable called speed, which for the purposes used here is the exact same as the one up here. It just it means move at 100 pixels per second, basically. And then we have this weird looking thing here, which is a window event. Window.onKeyDown is a function that is called by the browser whenever a keyboard key is pressed down. And we can sort of override this function and give it our own functionality, which is neat. So what we do here is we take in E, which is a window event, and this E, because it's a key, contains information about the key that was pressed. So we get that using e.keycode. And I just sort of have these already written out, but this is W, A, S, and D. For the most part, the key code of the key pressed is just going to be the ASCII value of that letter, of like the capital letter. So A, you can see, is 65. But for things like control, which I mentioned here, that doesn't have an ASCII character, so it's a little weird. There's a link to a website here that I use pretty frequently. And if you just press any key, it'll tell you what the e.keycode value is for that. So like if I press left control, apparently that's 17. And if I press A, 65, W, 87, S, 83, and D, 68, which is exactly what I have written here. So all this does is it, whenever a key is pressed, if the key code is W, A, S, or D, it will move the player appropriately. So let's check this out. So I'm holding down the D key right now, and I'm moving to the right. I can hold down S and I move down. I can hold down A and I move left. W and I move up. So there are two really big problems with this. First of all, it's really jittery and it's just kind of weird. And second of all, you can't move in two directions at the same time, which is pretty lame. So the reason for the jitter, I'll explain that first, is there is the way that the window, the window.onKeyDown function is called, is when you first press a key, this function is called. Then it waits a little bit, and if that key is still being held down, it will basically call this function in a loop until the key is released. The problem is that the speed at which this function is called is slower than our game loop is running, which means that we don't get smooth movement. So if I sort of go back here and I stop him and then I hold down a key, you can see he moves a little bit and there's an initial delay and then he moves pretty fast, right? But it's still clearly jittery. And that's the reason for that, is that the speed at which the on-key down function is being called is different from our game loop, which is not bad. The goal, one really big goal, important goal, is to minimize or take out altogether any sort of reliance on frame rate at all, which is very possible. The other problem is that he only moves when a key is actually pressed, which I guess that's sort of related to what I was saying, is that the speed of this function is slower than our update loop. And that's not good. We want to, whenever a key is pressed, we want to say, okay, until this key is released, my player should be moving. Not just when the window intercepts this key event, but until it's actually released. And in order to do that, we have to store the state of the keys that we're interested in from frame to frame. So I'm going to add this object here called keys to my global object. And this just stores 4 smaller objects, W, A, S, and D. Each of them have a field for the key code, the relevant key code, and a Boolean saying whether or not they are currently being pressed. All right. And then now, first thing to do actually, before we move on, is take all this chunk of code at the bottom of main and just delete that. We're not going to use that. Make sure you still have the update call though. Okay, so we have this new onKeyDown function here. I'll copy that, and I'll put this in global.js just for organization. Don't want to clutter up our main.js. So this sort of complicated looking loop, it basically just says for every one of these objects, if this code number matches the code number of the key being pressed, then change that object's pressed value to true. Very simple. So this says when a key is pressed, set its pressed value to true. And similarly, we need one that says when a key is released, the window.onKeyUp function set its pressed value to false. Otherwise, the first time you press a key, this will get set, and then it'll never get unset. So you'd be stuck like moving to the left forever or something. Okay, now in our main function, in our loop, we can move our player using these variables in a frame-independent way. So I'll just stick this between these two calls here. I'm using the same speed, 100 times the delta over 1,000. And then this is just it makes it pretty. It uses the fact that you can use, in JavaScript, you can use Boolean values as integer values. So d.pressed, if that is true, and a is false, then we have 1 minus 0, which is 1, which means add a positive multiple of speed to x, which means move to the right. Whereas if a is pressed and d is not, we have 0 minus 1, which is negative 1 times speed. And when you add a negative number, it's the same as subtracting, so it means move to the left. So yeah, this is just a pretty way to say move x if you're pressing a and d, and move y if you're pressing w and s. So we can go ahead and test this. And there we go. Very smooth movement. There is an issue with this, one last one. It's really easy to fix. And the problem is if we are moving in x alone, it's perfect. If we're moving in y alone, it's also perfect. But if we're moving up and to the right or up and to the left, you can notice you move faster when you're doing that. And that is just the Pythagorean theorem. If you have something moving in the x, 1 unit, and also something moving in the y, 1 unit, which is what happens when you move up and to the right, then the total distance traveled is square root of 2. Or square root of 1 squared plus 1 squared, square root of 2. And the solution for this, I'm just going to talk about in this case where we're basically dealing with 8-directional movement, right? It's sort of like a Zelda game. You can just move like this. You can't rotate your character or anything. Then it gets a little more complicated. It's still the same general principle, but for now we'll just say I can only move in 8 directions. And when I'm moving in 2 directions at the same time, I'm always moving at a 45-degree angle. The reason for that is that the speed for our x and the speed for our y are the same. So we're always going to have you know, one movement unit in the X and one movement unit in the Y. We're never going to have one in the X and like two in the Y, which would give us some really weird value, right? So we're always moving at a 45-degree angle, which means all we have to do is check whether or not we're moving in both axes, which is really simple. And if we are, we divide the movement speed for that frame by the square root of 2. Very, very simple. So that's what this little loop here, or this little, not loop, if statement does here. I'm just going to go ahead and copy this, just so I don't make any dumb mistakes. Okay, so we store the target speed outside of the loop, and then each frame we have an adjusted speed, which we start by multiplying by the frame delta, same as we were before. But then we have this if statement that says if we're moving up or we're moving down, and we're moving left or we're moving right, then we multiply the adjusted speed by 1 over the square root of 2. That's what global.r square root 2 is. So I'll go ahead and add that really quick. R square root 2, 1 over math dot square root of 2. And the reason I do it this way is basically efficiency. In this case, it doesn't matter like at all, but it's a good practice to avoid division when you can. And it's an especially good practice to avoid square root when you can. And so by pre-calculating this value of 1 over the square root of 2, every frame we just have to do a multiplication instead of a division and or a square root. So this is, you know, technically more efficient, but when we're only doing 1, it doesn't really matter. I just thought I would mention that. So then instead of doing tile.x plus equals speed, we do the adjusted speed, which now accounts for both the frame delta and the 2-axis movement problem. So if I refresh this and run it, you can now see that based on the movement of the red squares around us, it's the same speed no matter which of the 8 directions we're moving in, which is perfect. Okay, so we're briefly going to talk about mouse input. We're not actually going to use it though. I just want to show you that this sort of concept of saving the state of some arbitrary input device is useful for more than just the keyboard. We're going to do that for the mouse as well. So I'll add this mouse object to global, similar to keys, except this time it just stores an X and Y, which will be the position of the pointer, the cursor, and the button that's being pressed down, where -1 means that no button is being pressed down. Then we just intercept these very similar events on mouse down instead of on key down, and on mouse up instead of on key up to control the button. And then on mouse move, there's a little bit of magic going on there, I'll explain, and then on context menu, I'll explain as well. So let's go ahead and copy this, and I will put that underneath our on key up. So we should have just this big list of window events at the bottom. So like I said, the on mouse down function, it just sets the mouse button equal to e.button, the button that the event was triggered by. And then on mouse up, we just set the button back to -1, which means that no mouse button is being held down. On mouse move, I did a little bit of magic where I get the bounding client rect from our canvas, which is sort of a window property. And all this little bit of math does is it takes the X coordinate and Y coordinate of the cursor, and it makes them relative to the top left corner of our canvas. So let's test this really quickly. In the main loop, we can do a console.log on global.mouse every frame. And then if we go back and refresh here, you'll see when you move your cursor to the top left, you have X of 0 and Y of 0, which is perfect. And when you move to the bottom right, you have X of 800 and Y of 800, which is perfect. And if we didn't have that, those would be slightly skewed. It's not necessary, but because we're not using it. But if we were using this, that would definitely be necessary. Yeah, so that's it for the mouse. We're not actually going to use it. We're just going to use the keys. So the next thing we're talking about is collision prevention. So this is an extremely detailed topic, and I'm by no means claiming to have solved it or whatever. Um, and even for the super simple example of rectangles that we're using, so because we're only using rectangles and because none of our rectangles rotate, we can use I guess it's an algorithm called AABB, or axis aligned bounding box. So axis aligned, meaning that the two things you're testing collision for are not rotated relative to each other, which is exactly how our rectangles are, and bounding box, meaning that you check sort of the outer limits of your object, which is very easy for a rectangle because if you remember, in our tile class, the outer limits are actually how we define it in the first place, the top left coordinate and the width and the height. So we can get sort of the extremes of this shape with some very simple math. So this it will not work for rotated rectangles, and it will not work for non-rectangles. So it's super specific, but it works extremely well, and it's very fast and very easy to understand. So we're just going to run with this. If you're interested, I mention here a side note. If you're looking for an algorithm that works for sort of an arbitrary polygon, as long as it is a convex polygon, you can Google separated axis theorem. And this is one that it's an implementation of collision resolution that is very linear algebra heavy. I've never actually implemented it. It's pretty simple. Like, I've read about it. It's a pretty simple concept, but like I said, my simple version here works for pretty much most of everything you'll need for simple 2D games. So I've never even needed to implement this. So yeah, we're just going to look at AABB. So first we're going to look at just a straight up out of the box implementation where we won't resolve any collisions. We'll just print something to the console if a collision is detected. And that'll just make sure that we'll sort of build from that so that you understand how the check works, and then we'll work on resolving it. So let's do this. I mentioned here again that our coordinate system, positive x is to the right and positive y is down the screen. So it's easiest to think of the start of a rectangle being the top left corner. Now we can use these variables that we store here in our tile, the top left and the width and the height, to get the minimum and maximum values of this tile on both axes. So the minimum x value, assuming non-negative width and height, which we have, the minimum x value is just going to be x, the top left corner, and the maximum x value is going to be x plus the width. Same for the y. Minimum y is y, and maximum y is y plus the height. Now I will copy this little bit of code here just to check if there's an intersection, and I will paste this function into global.js. So let me explain a bit about this, because it looks really complicated, but it's pretty much not. It's just put into code what I was just saying. So we have and I could probably draw this out maybe in Paint. If a.x, so a and b are two tiles. We're just going to assume that the user passes a tile to A and a tile to B. If the minimum x of A, the left side of A, is less than the right side of B, and the maximum x of A is greater than the left side of B, we have overlap on the x-axis. So what this could look like is, say, red is A and blue is B. In this case, we have the left side of A, so over here, is less than the right side of B, which is over here, so that checks out. And the right side of A is greater than the left side of B. So the right side of A is greater than the left side of B. And remember that positive x is this way. So that checks out. In this case, we have collision, or not collision, but overlap on the x-axis. But you can tell that these two objects aren't actually colliding. They would be colliding if I moved this this box down like this. And all I've done here is say, okay, well now there's obviously overlap on the x-axis, but there's also overlap on the y-axis. That's all this check does. Checks that there's overlap on the x and there's overlap on the y. So we can use this in our main.js. Just do a quick console.log of global.intersection, and we will test tile, which is our player. And I'm going to have to give a name to one of these other objects up here. I'll call this box. Box equals new tile. And that is the small one. It's 50 by 50. So if there's an intersection between tile and box, it will log true because this returns a Boolean. Otherwise, it will log false. So let's go ahead and check that. You can see we start inside the small box, so it's logging true a bunch. Now we're outside, so it's false. You can see true again. This is a little bit weird because my player sprite doesn't take up the entire size of the rectangle. But yeah, we can see that if we're just overlap on the x-axis, like I said, it logs false, which is good. If we just have overlap on the y-axis, it also logs false, but as soon as at least one of the corners of the player is inside this other box, it starts logging true, which is perfect. So now we've detected a collision, and that's the first step. The next step is to actually resolve these collisions, and this is much trickier, but it sort of builds off of these same checks that we just used. So I've got a huge function here, comparatively huge for this project, called fixIntersection. I'm just going to go ahead and copy and paste that in here, and let's talk about it. So you'll notice that these two if statements are the exact same checks that we used in our previous function. So this one just says if there's overlap on the x-axis between these two tiles. Then we get into more specific checks. And this one just says if there's overlap on the y-axis, same thing. So I'm just going to talk about this one because everything I say about this one is true for this one. You just flip x, y, and width height. Okay, so if there is overlap on the x-axis, and there is also the y maximum of A, so the bottom side of A, is greater than or beneath the bottom side of B, or sorry, the top side of B, and I'll draw this in a minute, and the bottom side of B is less than the y midpoint, sorry, the bottom side of A is less than the y midpoint of B, we resolve the collision. So let's look at this. So we have, I'll do my headphones died again. I'm back. All right, so A is red again, and B is blue. So we already know, I guess I should draw this differently. We already know that there is x-axis overlap, right? That's the only way we get to this check, is if there's x-axis overlap. So now we need to check that the bottom side of y is greater than the top side of B, and the bottom side of y is also less than the midpoint of B. So this is sort of a janky approximation that will improve in just a minute. But we can see here that there's no collision, right? But if I sort of move A down just a bit, now we can see that the bottom side of A, this one, is beneath the top side of B, this one. Beneath meaning greater than, because positive y is downwards. So then this check would run. This if statement would be true, and so this would execute. And this says a.y, or the top of A, is equal to the top of B minus the height of A, which essentially means, it's just simple algebra, it means position A such that the bottom of A is just touching the top of B, which is exactly what we want, because that'll make it look like A cannot pass through the top of B. And the reason we have to do, I guess I'll just explain it, even though we're going to change it in just a minute. The reason we have to do this check of if the bottom of A is less than this midpoint is, say we had, this is going to get real messy, but say we had A like way down here. Then clearly the bottom of A is greater than the top of B, but if this check runs, then A is going to shoot way back up here, because that's what this does. This sets it so the bottom of A just touches the top of B no matter what. So we need to make sure that the bottom of A is greater than the top of B within a reasonable range, pretty much. That's all that does. And then we do the same for the top of A and the bottom of B. So I'm going to go ahead and erase all of this mess. So we have B, and we have A. So there is x-axis overlap once again. And now we check if the top of A is less than the bottom of B. So this is the top of A. If that is less than the bottom of B, which is this, and the top of A is greater than the y midpoint of B, which is here, then we pop this back out so that the top of A just touches the bottom of B. That is a pretty weird way to draw that, but there you go. It'll do that. And again, remember that positive y is downwards. Okay, and then this thing does the same thing, but just for the left and right side. So now using this, we can get rid of testing if there's an intersection. We know that works. We can instead do global.fix intersection between tile and our box. Oops. And if we run this now, we should be unable to pass through the box. So I'm holding S down, and over here I'm going to hold A down, or sorry, D down. So I just can't move through it. You will notice though that it's not perfect. So if I go to the right side here and I start holding left to move, it sort of jumps to the bottom side. And the reasoning for this is that the order that we attempt to resolve the collision, the order that we do these in, is sort of just arbitrary, right? They're not based on anything. We're just checking them in some random order. And what that means is that if more than one of these conditions is fulfilled, whichever one executes first will end up happening, even if that's the one that doesn't make the most sense. So that's exactly what's going on here, is where obviously in this case it would make the most sense for the player to resolve to the right, but instead it resolves to the bottom just because that check happens first, which is not great. But this does work, you know, more or less. It's pretty bad, but it's basic collision, which is a start for sure. So now we're quickly going to talk about, this is sort of the last part of the talk, is just a custom implementation of this, which attempts to predict the direction from which a collision is most likely to happen. Excuse me. And using that prediction, we can then resolve the collision in a non-arbitrary order, which is the problem we're having right now. So I'm going to go ahead and delete all of this code. We don't need that anymore. The first thing to do is copy this little array here, which calculates the distance in pixels between opposing sides of A and B. So the bottom of A and the top of B, the right of A and the left of B, top of A and bottom of B, so on. And this is how we are going to predict which side it's going to happen from. We're going to calculate these four values, and then depending on which of these four is the smallest, we will resolve only that type of collision, if it exists at all. So we have those four. Now this little loop here, very simple, just actually gives us the index of the minimum collision. In this case, we're not worried about the distance of minimum of the minimum distance between any two pairs of side. We're not worried about the distance. We're worried about which pair of sides it actually is, because that will tell us which pair of sides a collision is most likely to happen between. So we get the index of that, and then knowing that index, we can sort of take our previous checks and modify them a little bit, where we have, if there's overlap on the x-axis and the minimum index is 0, which means the bottom of A and the top of B, and the bottom of A is below the top of B, then we position A right on top of B. So that's what we were doing before, except now we have removed sort of the arbitrary order that we did it in, as well as the arbitrary check of, is it greater than the y-axis midpoint of B. We don't have that anymore. And then we have a similar check for popping A out to the bottom of B with min equals 2. And then basically you just cookie cutter, replace x with y and width with height, and change the indices a bit. And we now have resolution for the left and right sides as well. So we can check this. We already have fix intersection written in our main function. So we can go ahead and refresh the page and run. And you should notice absolutely no clipping at all. I'm really quickly, I'm going to get a better sprite to test this with, because that's kind of the whole point. I'll just make my player sprite take up the whole actual box. Okay, so here's my player, the green one. And no matter how close I am to the corner, it still resolves it in the correct direction. Unlike last time, where it was sort of, if I was here, it would like just randomly clip to the bottom. So there you go. That works for that. This is not the most comprehensive implementation of AABB. There's one that this is the most complicated one I've ever used. As far as I know, I kind of came up with this one. I'm sure it's been used before elsewhere. But the one I have seen, other than this just sort of very basic one that we wrote at first, uses some linear algebra, and it's a bit more complicated, so I didn't want to talk about that today. But yeah, this is all we need to do. One thing I guess I didn't really mention is that this function, because it takes into account the width and height of each of the boxes or each of the tiles individually, it works for arbitrarily sized rectangles. They don't have to be, just squares, so I can go ahead and make this one a bit wider. And you can see that it works for that. And I can make the player like some weird dimensions, and it'll work just fine. As long as they are rectangles and they're not rotated relative to one another, this will work perfectly. So we've reached the conclusion. This is the point where we did it in about an hour and a half, which is pretty good. Usually I ramble a lot more. But I'd just like to thank you. I love teaching stuff like this, so when ACM said, hey, we need someone to do a game dev workshop, I was like totally into it. And hopefully you enjoyed it too. Hopefully also it wasn't too much of a bummer to you that I'm not talking about or using any specific or maybe relevant technologies like Unity to actually make a game. I just figured that this is sort of how I learned the basics of game programming. And I think that no matter what system you're using, it's very important to understand the issues you have. Even if, like for something as complicated as Unity, I couldn't even begin to tell you how they've implemented the camera or the renderer system or something like that. But I know that the problem is there of having to draw an arbitrary number of things each frame and organize that data, and I've considered it. And that can help you just understand. And the more things like this that you go through, it's literally just experience. The more programming that you do of this kind, the more and more things you'll start to understand, even in modern day games. So yeah, if you have any more like specific questions than I went over in this talk, feel free to ask them in the chat now. I'd be happy to answer. You can message me on Discord. Here's my tag. And it doesn't have to be just about JavaScript. It can be about whatever. I will let you know, I'm no expert on this by any means, but I do have some experience, and I would love to help you out. Um, there's also a zip file for if you want to sort of come back to this project, tomorrow or next week or whatever, if you forgot something or wanted to learn more about something, because no one can learn everything the first time through. So this page will remain up for you as long as you have the link. And there's just a link here to download the zip file. And this has all of the code commented as well. So if I sort of didn't explain some things or explain them poorly, it's probably explained better in the zip file there. So you can just go ahead and download that and open it in your editor of choice. But yeah, so does anyone have any specific questions they want to ask, or something that I didn't talk enough about or whatever? This is the awkward part because there's no one actually talking to me. I just have to wait for the stream to catch up and you guys to type. All right. Well, it looks like there are no questions. So yeah, I guess this is it. Just again, feel free to reach out to me on Discord. If you can't find me, I'm sure you can find some of the ACM heads, and they know who I am now, so they can point you to me. But yeah, I look forward to hearing from some of you guys, and thanks for attending.